So in the last video, we talked a lot about how we could relate external forces um, to the stress at a given point, or to the concentrated forces at a given point due to the internal pressures or the internal stresses. In this video, what we're going to talk about is how we can define the stress at any given point using a technique called the stress element. Okay, so our stress element here, all right, we'll have 6 faces, okay? It'll have what we'll determine as our front planes, okay? Or our back planes, right? So our front planes are going to be the front surface here, the right-hand side of our bar here, and the top surface of our of our cube. Right, while the back planes are going to be the left-hand side of our, or the back side of our part, which I'll call label 4 here. The bottom of our box, or the left-hand side of our box, which I'll label our cube, I'll label as 5, and then the bottom of the box, which I'll label as 6. So for each of these faces, these 6 faces, they'll have a normal stress associated with them, and they'll have 2 tangential stresses or shear stresses. So for the front face, it's going to be normal to the z-axis, so it'll have a normal stress of sigma zz, right? And it'll have 2 shear stresses. It will have a shear stress along the y-axis and the shear stress along the x-axis. So since it is a front plane, it will have we'll draw its shear stress as being positive along the positive y-axis. So this would be tzy, and then it will have tz or tau zx. All right. So those are the 3 internal stresses along, or those are the 3 stresses along the positive plane along the z-axis. Similar on the right-hand side of the cube, our normal stress would be going along the x-axis, so it would be sigma xx, right? And then we would have 2 shear stresses. We would have tau zx, oh sorry, xz, oh sorry, xy, and then we have tau x z. All right, and then our last element, our last face of our cube is going to be the top of the cube, all right, which will be normal to the y, sigma yy. All right, and then I'll have 2 positive tangential stresses. It would be tau y x and tau yz. All right, so you can repeat this process for the rear and back planes of the element. So if we start on the back surface, we would again have sigma zz. Please notice that for the rear or the back planes, the positive notation is going to be along the negative axes. So we're going to have tau zx, and we're going to have tau zy as well on this back plane. Okay, so tau zx is going to be going along the negative x-axis. All right, and then tau zy is going to be going along the negative y-axis. So I'm going to redraw these labels here. So this would be tau zy y, and this would be tau zx. So for the left-hand side of our box, we would have the x-axis is normal to it, so we'll have sigma xx. Notice that the positive direction for the back plane is going to be on the along the negative x-axis, and we'd also have tau xy and tau xz. here. All right, and then the last is the bottom plane, which we'll have sigma yy, should be going along the negative y-axis, and then we have tau yx, and we'll have tau yz. All right. All right. So those are all of our stress elements here. All right. So if we look at these all right, is we will have is that we can take all of these different stresses, all right, and we can combine them into a single matrix, which we'll call our state of our stress. So this stress matrix, which sometimes might be referred to as sigma ij, all right, it's gonna have 9 components to it, all right. So the first component, or the first index, will be our rows. So this would be, all right, and then our second index will be our columns. Okay. So for our first element, we would have, so our first index will be x, well, right, x, y, and z, and we'll write our x, y, and z on the top, all right, and we'll have a 3 by 3 matrix. So what we'll end up getting is we'll get sigma xx for our first component. For the second component, it would be equal to, since it has different elements, we're going to label it as a shear stress, and it'll be tau xy. Then our third component of this of the stress matrix is going to be equal to tau xz. All right, and we're just going to follow this pattern out until we have all the components of our stress matrix all labeled. So we will have tau yx, we will have sigma yy, we will have tau yz here, and then on our last row we will have tau zx, we will have tau zy, and we will have sigma zz. Right? So for any point, based off this definition, we have 9 unique stress components at any point. All right. So what we're going to do now is we're going to look at the stress element a little bit closer. All right. And we're going to see if we can relate any of these individual elements within the matrix. All right. So if we look at just the, if we draw a axis through the center of our element and we label this axis as the z-axis, okay? We're going to have all of our internal stresses, sigma xx, our normal stresses, sigma xx, sigma yy, sigma zz, all right, and then also our shear stresses that go through the z-axis as well. We can ignore all of them because they will go through the z-axis. So if we take the moment about the z-axis, they wouldn't contribute to the moment, so we can ignore them. So if we do some statics here, and we take the moment about the z-axis using just our various stresses here. So we're going to have tau. So we have tau xy on the back plane of our cube, all right? And then we have on the other side of the cube, we'll have tau xy plus any change due to the shear stress, in the shear stress along delta x. So we'll call that change in shear stress delta tau xy. All right. So if we take tau xy and we multiply it by the area of the side of our element, and we multiply it by the moment arm to get to the center of our cube, we'd end up creating a moment due to that shear stress. All right. And we can repeat that process for the right-hand side of our element as well. Now, we can do the same thing, but on the top of the cube. If we look at, we're going to have on the top of the, on the bottom of the cube, we're going to have tau, tau yx. All right, and then on the top of the cube, we're going to have tau yx plus delta tau yx. All right, if we multiply those shear stresses by the differential areas, we would get our forces. All right, and since if we use the right-hand rule, what we notice is that these would create a a clockwise rotation about the z-axis. So it's going to be a negative moment caused by those stresses. All right, so using this equation, we can divide all of the terms or both sides of the equations by delta x, delta x, delta y, delta z, and can combine all of our like terms. All right. So if we do that, what we end up getting is we get tau xy plus delta tau xy over 2 is going to be equal to tau yx plus tau yx divided by 2. So as our differential element becomes very, very small, the change in our shear stresses, tau xy and delta tau yx, are going to approach 0. So these terms would both go to 0. We're left with this identity here. So we can say that the shear stress on the right-hand side of our element and the left-hand side of our element would be equal to the shear stress on the bottom of our element and the top of our element along the x and y directions. Right? In a similar fashion, we can sum the moments about the x-axis and the y-axis to prove that tau yz is equal to tau zy and tau xz is equal to tau zx. So we went from having 9 unique values within our stress element to only 6. So our normal stresses are unique, all right, and then we will have our shear stresses are equal, right? So, all right, and all right, so those are the equal terms, all right. So when we're solving for the state of stress, we only need to solve for, if we know these 6 components, we can then define the state of stress for any point within any engineering component.